Hello students, hope you all are well. Now students, in the previous lecture we have studied about Gauss's law, and now today in this lecture we will study the application of Gauss's law. The learning objective of this topic are, after the completion of the topic, students will be able to find the electric field of a given situation using Gauss's law. Now, the very first application of Gauss's law is to find electric field intensity due to an infinite long straight charged wire. Before starting with the article, let me introduce you first with Coulomb's law. Beta, Coulomb's law is applicable for two or more charges. Now, when the situation is that we have continuous charge distribution, then we have to use Gauss's law. So here, in this given situation, we have a long straight wire. This you can see, a long straight wire is there, which is positively charged. This hole is positively charged. Now we have to find the electric field intensity of this given wire. Now for this, you can see, since the wire is positively charged, and therefore the electric field will be radially outward, that is perpendicularly outward. So you can see the electric field intensity along this direction and along this direction. It is perpendicularly outward. Now, to use Gauss's law, we have to first consider a hypothetical Gaussian surface. Now, by symmetry, we will take it to be a closed cylinder, this green color, which is having radius r and length L. Now you all aware of Gauss's law. Now from Gauss's law, that is electric flux is equal to E dot ds full integration, which is equal to q upon epsilon naught. Now we will divide this whole surface, that is E dot ds, into whole integration into different parts. That is E ds A is this, E ds B is this, and E ds C, which is this. Now, E dot ds A, it will be equal to E ds cos 90. Look here at this A figure. E is perpendicularly outward, and ds you have to give the direction perpendicularly outwards, that is for area vector, and hence the angle between E and ds is 90 degree, which is 90 degree over here. Now similarly for B also, E is perpendicularly outward for this wire, and the surface area is here ds. It is also to be taken, the direction is to be taken perpendicularly outward, and hence the angle is 90. Therefore, we will have cos 90 over here. Now look at the figure C. At point C, E is perpendicularly outward, and you have to take this area to be also perpendicularly outward. Therefore, the angle is 0, and hence angle is here 0. So cos 90 becomes 0, and E ds cos 0 becomes 1. So taking E outside, integration will be at ds, and this is curved surface area, which is equal to, for a cylinder it is 2 pi RL. Now next, since the wire which we have given, it is having continuous charge distribution. So instead of Q, what we have to consider? We have to consider linear charge density, that is lambda. So instead of Q, we will get lambda L, because as you know, linear charge density is equal to charge upon length, that you have read in the first subunit of electrostatics. From the previous slide, we have got that E into 2 pi r is equal to lambda L upon epsilon naught. LL gets cancelled, and we get E is equal to 1 upon 2 pi epsilon naught lambda by r, or In terms of 4, as we have the constant 1 upon 4 pi epsilon naught, it becomes 2 lambda upon r. Now this is the magnitude form, and if we want to write in the vector form, then E vector will be equal to 1 upon 4 pi epsilon naught, 2 lambda upon r, and r unit vector. Why r unit vector? Because it indicates the direction which is perpendicularly outward. Since the wire is positively charged, and hence the direction will be, this r unit vector will be perpendicularly outward, and in case if it is a negatively charged wire, then the direction will be radially inwards. So this was the first application. Now let's study the second application. The second application is to find the electric field intensity due to an infinitely long thin plane sheet of charge. Now in the previous case we were having a thin long wire. In this case we are having an infinite long sheet. You all can see here, this is a sheet which is positively charged, this sheet. Now first of all, we have to consider a Gaussian surface, a hypothetical Gaussian surface, that is an imaginary hypothetical Gaussian surface, and again by symmetry we will consider this to be a cylinder. So applying Gauss's law, that is phi is equal to E dot ds whole integration, which will be equal to 1 upon epsilon naught times the total charge enclosed, and again dividing this E ds into 3 parts, that is the Gaussian surface into 3 parts, again into this A, this B and this C. So E dot ds A, E dot ds B, E dot ds C. Now look here for the first figure, that is for point A. E is, now since this is a positively charged sheet, therefore the direction will be again radially outwards, that is the direction of electric field. Again you can have a look, E is always radially outward. Now for point A, since E is along this direction, now the surface area of this side of the Gaussian surface, this ds, it will also be perpendicularly outward, and hence the direction between E ds will be 0. So here we will get 0. Now look at the second figure, that is E ds B. Similarly like A, here we have B. Again E and ds, they will be in the same direction. So again it will be 0. So A and B here will be similar, because in both A and B, E and ds, they are acting in the same direction, and hence it will be cos 0. Now look for the third curved surface of this cylinder, that is point C. E is perpendicularly outward for this plane sheet, and for this curved surface area, the direction of area vector will be perpendicularly outward, and hence angle is 90 degree. Therefore we have 90 degree over here. Now this get cancelled because cos 90 is 0, so it will be 0. So we will have the electric field because of A and B, that will be 2E, and we will integrate it for the surface area, that is ds. Now so here the area will be this and this pink circle, so it will be 4 pi, it will be pi r square. Now next, again we have to consider, because it is continuous charge distribution, since it is continuous charge distribution, so we have to consider surface charge density, and surface charge density that you have read in first subunit also, that is surface charge density sigma is equal to charge upon area, that is sigma is equal to charge upon area. So Q here will be sigma into area. So sigma into area is pi r square, it gets cancelled, and we have E is equal to sigma upon 2 epsilon naught, which is the scalar form or the magnitude for electric field due to a plane charged sheet. And if we want to write in vector form, we will give the direction, and here I vector indicates the direction of electric field, which is perpendicularly outward because it is positively charged, and if it is negatively charged, it will be inside. So at last if we have a thick sheet instead of single thin sheet, we have a thick sheet, then the formula gets modified and the electric field becomes E is equal to sigma upon epsilon naught, because now it is thick sheet. Now we will have the electric field in both the directions, and hence it gets added, this sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, which gets added, and we get the result, that is electric field is equal to sigma upon epsilon naught for thick sheet. I hope it is clear, and in the next lecture also we will study about the further applications of Gauss's law. Thank you. Till then, stay healthy, stay blessed.